Um, so we'll begin with number 23, question type number 23, wherein we will discuss the kinematics of circular motion, and we'll also touch upon the elliptical motion a little bit. Once again, we will study the characteristic of uniform and non-uniform circular motion, and we'll also touch upon the elliptical motion. Okay. So, and when I talk about we'll study the motion, what are we going to talk about? We will try and study the velocity, the acceleration, the relationship between them, and let's see. I think those would be the primary focus for this study. So let's begin. Now, before we get started, Chavi Bida, are you comfortable with circular motion a little bit? Have you studied the circular motion in your classes yet? I'm sure you have, right?
Yes, sir. But मुझे उसमें एक दो doubts थे, but I think like once you do it, if I can like still, then I'll tell you if it is still isn't cleared or not.
Okay, okay. So let's begin. We will have some fun with the circular motion to begin with. Let me see if I can enlarge the picture here, image. That'll make it easier. There we go. Take it. So let's first talk about the uniform circular motion. Uniform circular motion. So uniform circular motion. What do we mean by word uniform? That the particle is moving in the around a circular path at uniform speed. Uniform speed. So let me first ask the question. Do you think the particle is under any kind of acceleration? The question is directed for now for Chavi. Beta, do you think the particle is under any acceleration if it is moving along a circular path at constant speed?
Yes, sir.
Okay. And what is the magnitude of the acceleration? And what is its direction?
So I think it would be like the rate of change of like angular velocity, right? So
Aha, this is interesting. So, Chavibita, you said the acceleration is equals to rate of change of angular velocity. Okay. Ruchika Beta, would you agree with that statement? Would you say that statement is correct? But that statement is not correct. Sure. Understand a couple of things about the circular motion. So let's start with the
Uniform speed means uniform angular velocity, right? Constant angular velocity.
That is correct. So uniform speed would mean uniform angular velocity. To understand this, let's start from the very basics. Let's work from the very basics. Okay. For that, let's say the particle is at certain point A. I'm going to call this point as A, and the particle is tracing the circular path in the anti-clockwise or counterclockwise direction. So at time t equals to 0, it is here. And let's say at some time, after some time dt, it is at this point. Right, Peter? So it has moved from this point to this point. And we call it B, and it is at B at time t plus dt. How much angle has it traced? It has traced an angle d theta. Is that right, beta? Chavi, is that right? No?
Yes, sir.
Okay. Let's call this distance that it traced along the circular path as ds. So let's write the relationship between ds, linear variable, and d theta, the angular variable. So for that, recall the definition of angle theta. How do we define angle theta? We say angle theta is defined as arc length divided by the distance r, divided by the radius r, or the radius of curvature r. Theta is s by r. So let's use that basic definition of angle in this scenario. So what do we have here? So we have d theta is equals to ds pi r. Any concern, any issue on this front? Yes, beta?
No, sir.
No concern. Okay. By the way, what is this ds in terms of dt? So how much is ds? So recall, speed was v. What is v? V is distance traveled. This is distance traveled. ds is the distance traveled. Speed is distance by time. ds by dt. So ds I can write as v dt. Correct, na beta? So I can write this as v dt. If I bring dt to the left, so I'll get d theta by dt is v by r. What is v again? V is the linear speed. Linear speed. I'm not talking about the velocity, which is a vector quantity. I'm talking about speed, which is a scalar quantity. So we have d theta by dt equals to v by r. Now, what is d theta by dt? Rate at which the particle is tracing the angle theta. In other words, how much angle it traces per second, d theta by dt. What is that? That is angular velocity. That's how we define angular velocity, even though we'll talk about this when we get to the rotation chapter. But this is a fairly basic definition that you must have touched upon in your previous classes as well. Any concern on this definition? Omega equals to d theta by dt. If not, you guys are okay with this relationship now? Omega is v by r. Omega is v by r. Any doubts on this front? Right? So now v, we said, is constant. Speed is constant. The particle was moving around the circle at a constant speed. In other words, we is saying v is constant, which means omega must be constant. Now, what is angular acceleration? Angular acceleration is defined as rate at which angular velocity is changing, d omega by dt. D omega by dt. Rate,
Oh, sir.
yes, ma'am.
So omega is essentially telling us how the rate at which the theta is changing.
At which the particle is tracing the angle theta. This is a new language, tracing the angle theta.
Yes, sir.
Okay. So let me just explain. So let's say, if you remember in your younger classes, the reason I say that is because our daughter is in a younger class, right? So she is learning about the angles and geometry and whatnot. And I noticed that the trick they use to draw an arc or a circle is to take a thread, right? And let's say you start from this point, you put the pencil there, and then the teacher will say, okay, trace an angle of 30 degrees, right? So they'll trace an angle of 30 degrees. So this is angle 30 degrees, right? So they make an angle of 30 degrees. So this is the distance through which they move the pencil. And in the process, you end up casting an angle of 30 degrees at the center of curvature. Now is the word clear? What do we mean by tracing the angle theta?
Yes, sir.
Angular velocity means, so let's take an example. Let's say angular velocity is 5 radians per second. 5 radians per second. Okay? Or let's say 1 radian per second. That'll be easier. So in 1 second, how much angle does it trace? It traces 1 radian angle. Right? 1 radian angle. And how much is 1 radian in degrees, Peter? Roughly? Roughly, just a rough number. How much is 1 radian in degrees? So if somebody says my omega is 1 radians per second, and if somebody asks you the question, how much angle the particle has traced in 1 second? So what would be the answer in degrees?
So 180 by pi, right? But
Right. So pi is, let's say 3.14. Let's say it is 3, just for the rough calculation purposes, right? So pi is 180 degrees. So 180 degrees divided by 3, that'll be close to about slightly less than 60 degrees. Correct now?
yes, sir.
Okay, good. So we are clear about the angular velocity, how much angle it is tracing. And by the way, angular velocity is a vector quantity. Now, Ruchika beta, can I ask you a quick question? By the way, is that clear beta? What I said, angular velocity is a vector quantity. We'll talk a little bit more about it in just a few moments. But are you guys aware that the angular velocity is a vector quantity?
Yes, sir.
Okay. Can you give me another example? By the way, so before I talk about the example of a non-vector quantity, what do we call as a vector quantity? Vector quantity is a quantity which has magnitude and direction, and it follows the laws of vector algebra. Right? Never forget the laws of vector algebra. You might have a quantity which has direction, which has magnitude, but may not be vector. Can you guys give me an example of such a quantity? Which has magnitude, which has direction, but it is not a vector quantity.
Current.
Current is not a vector quantity, yes. What about angular displacement? So if I say theta is 30 degrees in the counterclockwise, so I've given you the direction, right? But is it a vector quantity, thetas? Angular velocity is a vector quantity, but is angular displacement a vector quantity? It is not, right? So angular displacement is not a vector quantity. Why? It does not follow the law of the vector algebra. Which law? The commutative law, a plus b is not equals to b plus a. Right? So what do we mean by that? There are several examples that you can find. I think I have somewhere talked about the examples in one of the recorded videos there. But if you take a book, right, take a thick book. If you have something with you, you guys can do the experiment right now. But take a thick book, right? So by the reason I say thick book is when you say thick book, so then you have all the 3 dimensions. All are significant dimensions, right? The breadth, the length, and the thickness, right? Length, breadth, and the thickness. Now, if you were to rotate the book by, let's say, 90 degrees along one edge, right? And then rotate it around one of the other edges by 90 degrees, okay? So you will get into a certain, the book will get into a certain position. Yes, the book will attain a certain position. Now, switch the order of the rotation. First, rotate it about the edge that you rotated it the second time. Rotate it first now, and so basically you're switching the order of the rotation, and you will see that the book reaches in a different orientation. It's not the same orientation. Okay, clear? So the question sometimes kicks in, then why is angular velocity a vector quantity? Because after all, angular velocity is angular displacement by time, right? But when we define the angular velocity, we're talking about the way we define the instantaneous angular velocity is the differential angular displacement by time. So when you are moving things in differential, right? So let's say by small amounts, when you do the vector addition, then it becomes a vector. Right? When we're talking about large angular displacements, it is not a vector quantity. The last part, if it is confusing, then I would recommend that you guys read through the Resnick holiday if you have one, and try and see the example of the book that I'm talking about. They have nicely explained it. And you can do it many other ways as well, right? For example, stand straight, keep your hand by your sides, and keep your palms very open and be very conscious of where your palm is, right? So initially keep your palm pointed towards your legs. Now lift the lift your arm up at 90 degrees in you can choose any direction you like, right? And then rotate it by 90 degrees in the other direction. Now switch the order. You will see that your palm is not facing the right in the same direction as the first instance, right? So, and what is the key condition of a vector algebra? So if you add a plus b, it should be equals to b plus a. Okay, so I'm not going to spend too much time on that. You guys can do your study on your own. So let's come back to this discussion. If you have any doubts, yes, please do call me up, send me a WhatsApp message, or we'll talk in the next class. Let's come back to this discussion. So omega is V by R. Correct, Namita? Omega is V by R. Right?
Yes, sir.
Now, question is, which acceleration we talking about? We said it's a uniform acceleration. It's a uniform angular velocity. Does the particle still have acceleration? Well, as per the definition, acceleration is the rate of change of velocity. Right? Rate of change of velocity. Now let's look at the velocity vector. Has the velocity vector changed? So I'm going to use perhaps an empty space here. Here we go. So let me draw the circle again. The particle goes from here, this point, to this point. Not a very good circle. So I'm going to, or maybe I should have selected different points, but I think this is good enough. There we go, right? So initially at point A, my velocity vector is pointed like this, but here it's pointed like this. Correct now? Am I right?
Yes, sir.
So even though the magnitude of the velocity vector is not changing, its direction is changing. Well, if the direction is changing, magnitude is not changing, doesn't matter, but the vector is changing. It's not the same vector. If the vector is changing, then yes, we do have acceleration. So let's find out how much is the acceleration. So we said in time dt, this traces angle d theta. This is r. Now let me take these velocity vectors, right? So this v, and this is, let's say, magnitude is the same, but this is v plus dv vector. So let me, to find the dv vector, let me put them tail to tail, right? This is v, and this is my v plus dv. Magnitude is still the same, v and v for both, right? So from the initial position, let me call it the velocity vector 1, and this is the velocity vector 2. This is my velocity vector 1, this is 2. So you have gone from 1 to 2. Yes? Now, to get to 2, what vector should I add? This is what my dv is, correct? Then v plus dv, right? So this vector, so let me say, this is, let me call it v1, v2, magnitude is the same, right? So v1 magnitude is v, and v2 vector's magnitude is also v, only the direction has changed. So v2 is v1 plus dv. The reason I'm writing all this is because since you guys are new, just convince yourself that I have not done anything magical here where I said, hey, look in this direction and I've done something funny, right? Simple vector algebra. Correct, Nobita? Correct. So we have two vectors, v1 and v2. I want to find out how much is the change. How much is the dv? dv is v2 minus v1. So to find, so if I just redraw it, so there are two vectors, right? This is a, this is b. If I want to find vector a minus b, Which vector is this? This is the vector A minus B, no? Correct, beta? Convince yourself. Why do I say that? Well, as per the law of vector addition, this vector plus this vector should give me this vector. Well, it is, right? B plus A minus B plus B will cancel out. We'll get the A vector. Clear?
Yes, yes, sir.
Okay, so that's what I've done here, no? So let me redraw it a little bit bigger. Or if you guys are clear, then I'll leave it. I'll not do anything different.
Yes, sir, this is clear.
It's clear, no? And how much is the angle between the two? V1 and V2? Is it d theta? Because
Yes.
they are perpendicular, right? Both V1 and V2 are perpendicular to R. So if the position vector makes an angle d theta, then obviously they will also make an angle d theta. This angle is d theta. Okay. So once again, let me redraw it slightly bigger. This is what it is. This is V, this is V, this is dV. And this angle is d theta. Well, they're forming a triangle, so let's apply the same rule. dV is fairly small compared to V. So I'm going to use the definition of the angle, which is theta is equals to S by R. So d theta is dV by V. Right? For this triangle that I've made, this length is V, no? The side length or the radius of curvature is V. So d theta is dV by V, beta. Any doubt? No doubt?
No, sir.
Okay. And what was d theta for this triangle? For this triangle, your d theta is, let me write it here, d theta is ds by r. Correct? Yes, Peter?
Yes, sir. Yeah.
Okay, okay. So I'm going to equate the two. So what do we get from these two equations? So we get ds by r is equals to dv by v. I'm going to bring v to the left. So it's v by r into ds is equals to dv. I'm going to divide on both sides by dt. We get ds by dt is equals to dv by dt. Right? So ds by dt, speed by distances. Distance by time is speed. This is v. Another v. So can I say v square instead of writing v separately? And what is dv by dt? By the way, this is change in, I'm not going to put, because we're dealing with the magnitudes here, I'm going to keep it aside. dv by dt is the acceleration. And what is the direction of the acceleration? Look at where dv is pointed. dv is pointed towards the center. Right? dv, this vector, look at this vector. This vector is pointed towards the center. So this is your, what we refer to as centripetal acceleration, v square by r. Right? A is centripetal acceleration is v square by r. Clear? Yes, no, maybe?
Sir, एक बार आपने how did you get TTS pointed towards center once?
Okay, okay. Let's use the screen background for a second. Let's see if it brings out our if I were to translate this, right, just tell me if I am doing any, right, this vector is parallel to that vector, no?
Yes, sir.
Right? And this was my dv?
Yes, sir.
Correct, beta?
Oh, okay, sir. Got it. Yes, sir.
Right now?
Yes, sir.
Okay, so now we're gonna prove it algebraically. We're gonna prove everything, the direction, the magnitude of the centripetal acceleration algebraically. Ruchika beta, can you prove that for us, please? How would you prove it, beta? Same thing, centripetal acceleration, the in the vector form. In the vector form. Not to worry. So let's start, beta. So at any given time t, let me resolve this. Let me make some space. Let's say at time t equals to 0, at time t equals to 0, the particle was somewhere along what I define as my x-axis. Rather, I should say, let me define my x-axis passing through the particle's position at t equals to 0. That might be the right way to say it. Okay? And this is my x, this is my y. So this is my Cartesian coordinate axes, x and y. So at a time t, if the angular speed is omega, and what was omega? Omega is v by r. V is the linear speed. Then what will be the angle traced? This angle traced would be theta will be is equals to omega t, because what is omega? Omega is d theta by dt. Omega is constant, so I can write it by theta by t. So I can say theta is omega t. Anything funny in there? Everything makes sense?
Yes, sir.
Okay, good. So the particle is here at time t. Let's call it the position p. It is moving in this direction. Okay. The velocity vector is in this direction, magnitude is v. So the position vector is this one. What is a position vector? Position vector is a vector with its tail at the origin and head at the position of the particle. Okay? And the radius it's tracing is r. So can you guys help me write the position vector r? So can I write position vector r as position vector r as r cos theta I cap plus r sin theta j cap? Any concerns, any issues to that? Yes, beta?
Yes, sir.
Now, what is velocity? Well, velocity is rate at which the position vector is changing. Or I should say displacement by time, right? dr by dt. So let's differentiate it. And to differentiate, we need to know what theta is. So theta is, we said, omega t. So let me write omega t instead of theta in these two positions. Ruchika beta, you're okay now?
Yes, sir.
Yeah, beta. These small things, right? So I think you may have done them before, but still do pay attention. These small things, since you are there in the class, it always helps to absorb it. Just simply absorb it the way it is. Okay.
Yes, sir.
So dr by dt is what? It'll be, if you guys can help me differentiate. So it'll be r minus r omega sine omega t. Is everybody clear why I wrote that? Then it'll be r omega cos of omega t j cap. Yes, this is my velocity. Correct, Nabita? Yes, no?
Yes, sir.
Okay, so let's see if geometrically it makes sense or not. I've done it, right? I've just mechanically written my position vector and I've said v, but let's see if it makes sense for us. Okay, so let's go back to this diagram. This is my velocity vector v. So let me just kind of write it, let me declutter it a little bit. How much angle is this? If you guys can help me write it. What is this angle? How much is this angle? This is the angle that the velocity vector makes at time t with the vertical. How much is it? Ruchika beta, how much is it?
So theta.
Theta होगा ना? Yeah. Omega t. Because if you make theta 0, this angle also becomes 0. Because if the particle is here, the velocity vector is pointed along the vertical line, no? So that's how in my head, I double check things, right? So that's how I do a quick check. So now, if I know the magnitude is V, right? So what is if I know this vector, let me draw this vector here again. This is my V vector, magnitude is V, and angle it makes is omega t. Can I write it in the xy coordinate system? This is x, this is y. How would I write this vector? Won't I write it like this? Minus V sine omega t, because sine omega t is this component, right? Because it's the minus x direction, that's why the minus sign, right? Minus I cap, sorry, not j cap. And the vertical component is in this direction. That is V cos omega t. Correct, Namita? And what is V? We said V is omega r. So I can write this as minus r omega sine omega t plus r omega cos omega t j cap. Which is the same thing as what I wrote here, no? Is that clear?
Yes, sir.
Okay, good. So everybody clear?
Yes, sir.
Okay. Now let's quickly find acceleration vector. Acceleration vector is simply rate of change of the velocity vector, dv by dt. Velocity vector was rate of change of the position vector, dr by dt, dr being the displacement. So dv by dt redifferentiated, so you get minus r omega square cos omega t I cap plus, or rather minus r omega square sine omega t j cap. Any concerns? Okay. So if I can write it, I'm going to take omega square minus omega square out. What do I get? R cos omega t I cap plus r sine omega t j cap within the brackets. So if you look at this vector, this is nothing but the r vector, no? Right here. Just check. So I can write my acceleration vector as minus of some positive quantity, constant, because the reason I say omega square is constant is because omega is not changing with time. Angular velocity is constant, times the position vector r. Okay, now let's understand what this is telling us, right? So if you have a vector A, if I say minus A or minus 2A, how will that vector be? Right? In the parallel to the A vector, but in the opposite direction. Correct, no? Yes, beta? So this is minus some positive quantity times r cap. So what does it mean? That at this point, this was my r vector. So the acceleration vector is pointed towards the center.
Oh, okay, sir. Got it. Yes, sir.
Got it, no?
Yeah, sir.
Okay, so we have proved a couple of things. In fact, let me just talk about the last thing as well before I say yes, we have proved everything. What's the magnitude of this acceleration vector? Minus omega square r, magnitude of this vector. Minus omega square r, no? Well, magnitude of r vector is r, magnitude of a vector is minus omega square. Or in fact, let's not even worry about the minus sign. So I'm going to say omega square r. What is omega? Omega is v square, v by r. So we get v square by r, no? Just check. Just check and convince yourself. Yes, Peter?
Yes, sir.
Okay. So we have looked at a scenario of a particle moving along a circular path at constant speed, and we have been able to um, write down the expression for its position vector, its velocity vector, its acceleration vector. Um, and we have established that the magnitude of the acceleration vector is v square by r or omega square r. Now, this is one of the very important things in physics that you will encounter everywhere, no matter electrostatics, magnetics, it'll just keep coming. Modern physics, everywhere, centripetal acceleration is v square by r will keep showing up, not just in the your class 11 topics, but in class 12 topics as well. This is kind of one of the very, very fundamental things, right? So if there is any confusion, you guys have to ask me and I'll redraw these things. So we have looked at it both algebraically as well as geometrically. We have convinced ourselves that yes, when the particle is moving along the circular path, the velocity vector is changing with time. And if you look at the change in the vector, right? If you look at the change in the vector, it's always pointed towards the center. Convinced na Chavi beta?
Yes, sir.
Okay, okay. Now, Ruchika beta, can I engage you in some questions here regarding the non-uniform circular motion beta?
Yes, sir.
Okay, good. So now, let's say that the particle is having an angular acceleration, of 2 radians per second. Having the angular acceleration of 2 radians per second square. What does it mean, Chavi? That the in every second the angular velocity is changing by 2 radians, right? So if it at t equals to, if at some time it is let's say 5 radians per second, then just after 1 second it will become 7 radian per second. Correct?
Yes, sir.
Alpha is d omega by dt. If alpha is constant, then I can write this as delta omega by delta t. By the way, now if omega is changing, then v is also changing now. Speed, the linear speed with which it is moving, the linear speed of the motion around the circular path, that is changing now. Because v is equals to omega r, no?
Yes, sir.
Okay. So Ruchika, beta, question is, if you know the alpha, if the angular acceleration is alpha, then at this time, one acceleration is if the speed is v at that time, if the speed is v, then there is one acceleration for sure, v square by r. Correct, no, beta?
Yes, sir.
But there is another acceleration. What is that acceleration?
Zero alpha.
Alpha
So tangential acceleration.
tangential acceleration. So this is radial acceleration and then tangential acceleration. What's happening to my pen here? Let's change the direction. A tangential is alpha r. Beta, can you help me understand how I wrote this? AT is alpha r. Can you think? Wait a minute. Say yes, this is true. This is how you write it.
So we know as we can write the arc length as r into theta, and then we can differentiate it 2 times.
Okay, so we said theta is equals to s by r. Correct, Namita? So
Yes.
d theta by dt. Radius is not changing. Right? So the length ds by dt, which is v. We call this v, no? So omega is v by r. If you differentiate this again, what do you get? D omega is dv by r. Now, is there any difference between this dv and the previous dv that we wrote? that dv was the change in the direction of the velocity vector v, right? Change that was towards the center. What is this dv? Change in the magnitude of v. Change in the magnitude of v. Is that part clear?
Yes, sir.
Now, it might be slightly confusing, but the only way to remove that confusion is to redo all these steps that I've just done and make sure that you get it. Right? It'll take one or two times you do it yourself, and then all of a sudden the world starts to make sense again. Okay?
सर आप लास्ट वाला पार्ट एक बार फिर से बता सकते हैं?
Which part? This one?
So the difference, the V वाला.
Okay. So when we wrote dv there, right, earlier, so two ways the velocity vector can change, right? So you have this vector, it can grow in magnitude. This is dv.
अच्छा, okay, sir, yes.
Call it dv parallel. Okay. And then another scenario is that you can actually rotate it.
Yes, sir. Huh.
This is dv as well. Here the magnitude was the same, but this is dv. I'm going to call it dv perpendicular. Okay. So this is dv parallel that you're writing here. Remember how we arrived at this dv. This dv we said was theta. Dv perpendicular was v. What did we wrote there? So it was dv by v is equals to theta, right? So dv was v into theta. That's how we wrote it, or v d theta. This angle was d theta we wrote it. Correct, no? Yes, Peter? This on the other hand
Yes, sir.
is a change in its length.
सर तो इस वाले केस में दोनों होंगे ना? There'll be a perpendicular change also, and there'll be a change in the magnitude also.
Yes, yes, you're right. So in this scenario that we are looking at, you will have both. So the velocity vector is not only, so actually if it is here, then it becomes this after a while. Correct, no? In time dt. So what we are saying is, let's break it apart. Let's break it apart. So the change is, this angle is the d theta, right? And so if I just draw it like this, so this is my dv perpendicular, and this part is dv parallel, right? And because this is very small, so small means that these angles are still 90 degrees. D theta is very small angle, no? Remember what I told you? For any isosceles triangle, if this angle is very small and these are nearly 90 degrees, right? If this is 1 degree, then this is 89.5 degrees. Correct, no? Same thing here. So this is perpendicular. They're perpendicular. Even though the way I've drawn, they don't look like perpendicular, right? But this is what it is. Yes, Peter?
Yes, sir.
Now, why do I say that this is actually dv parallel? Because Peter, first of all, here we are writing theta equals to s by r. It's not a vector quantity. We're just dealing with distances, right? So so that's why I have just concluded that yes, this is actually what I'm writing is dv parallel. Okay, or the change in the magnitude of v. Okay. Okay. So I can write, this is my A tangential. So alpha is A tangential by R. So if I would write it here, A tangential is alpha R. So when the vector, when you have a non-uniform circular motion with v speed either increasing or decreasing, then at any instant, if you were to, if somebody asked you to write the overall acceleration, make sure that you do a vector sum of these two vectors. The net acceleration is in this direction. Is that clear? Yes.
Yes, sir. Huh, sir.
The next question is for Ruchika, and Chavi, you are more than welcome to attack that question, okay? So, beta Ruchika, for a pendulum which is oscillating about its mean position, so oscillating about its mean position, the at this point, what is the direction of the acceleration? What is the direction of acceleration here? And what is the direction of acceleration somewhere in the middle? A, B, and C. Direction of acceleration at point A when it has reached its maximum. This is theta maximum. What is the direction of the acceleration at point A? For this particle, for the bob at the end of the string.
Sir, so if we think about it, it will be so towards C. So I guess radially or not radially, but so it will be kind of the net acceleration will be towards C.
The net acceleration will be towards in this direction.
Yes, sir.
Tangential to it, right? Because there cannot be any acceleration in this direction, no? along the pendulum's rod or string, whatever you might have. And what is driving that acceleration? Is that the gravitational force?
Yes, sir.
Okay. What about C? What is the direction of the acceleration there?
So net acceleration will be 0 there.
Interesting. Chavi beta, would you agree that at point C, when it is fastest there, when it is its fastest at the bottommost point, the claim from Ruchika is that the acceleration is 0 there.
So horizontally होगी.
No, beta. There is no force acting at that point. There is no unbalanced force at C. At C, mg is vertically downwards, and the string is not going to allow it to move in that direction. So those vertical forces balance each other out. So there is no external force as such in the vertical, or is there? Is there a net vertical force in that direction?
No, sir.
Okay. Ruchika, what happened to this centripetal acceleration? Because after all, it is still following a curvature, no? It's going along a circular path, no? So now centripetal acceleration do not exist. Is it not changing its direction, beta? Continuously?
So it is.
It is, no?
Yes.
What is that acceleration in that direction? Whatever the speed is, if the speed is v at that time, v square by r, no? Because just in 1 second, just because the velocity is horizontal doesn't mean the acceleration have disappeared, no? In just a small microsecond, it is changing direction, no? It's continuously changing direction. There has to be that's what we learned just now. If a particle is moving along a circular path, whatever the circular path looks like, the reason I drew this pendulum is because this is a non-conventional circular path look and feel. But still, it is tracing that circular arc, so that at the very bottommost point, it has speed is maximum, so it must have a centripetal acceleration that must be pointed towards the center of the curvature. That is the hinge at which the rod of the pendulum is fixed. One end of the rod is fixed, right? So now, if the net acceleration is in the radial direction at that point, then at that point, so what does it mean? That the tension T minus the force mg in the downward direction must be equal to v square by r. That's it. Newton's second law, something we'll study in the next chapter. Net force is equals to mass times acceleration. Yes? Okay. Don't feel too bad about it. Sometimes these things skip. That's why the revision is important. Okay. So we are clear. What about B beta? B, will it have radial? See, here it had only had tangential. At A, only tangential. At C, only radial. Okay. There is no component of force along the horizontal direction. In the horizontal direction, there is no external force. That's why no tangential acceleration in that direction.
Sir, A radial क्यों नहीं है?
At A, because it has
Yeah.
stopped at that point. No? The pendulum, that's how it goes. No, pendulum moves, kind of oscillates, go to the farthest most point, stops there, and comes back. V
Yes.
is 0. When V is 0, V square by R must be 0. Yes.
Okay. Yes, sir.
Okay. Because as long as there is no V, there is no change in direction, right? It is not trying to change direction. So why would there be radial acceleration? It's only when the tangential acceleration starts to build up V, you start getting the radial acceleration. At B, it will have both the components. It will have radial acceleration as well as a tangential acceleration. Yes? Correct, Namita? So
हाँ sir.
this acceleration and it will have this acceleration. The net acceleration will be in this direction, somewhere in that direction. Not necessarily horizontal, but somewhere in that direction. Correct, no? I hope you guys are clear. Clear, yes, no?
Yes, sir.
Okay. Well, it has taken a little bit longer than anticipated, but this is an important important piece. So we should not. It was worth time well spent, right? Let's do a few questions here. JEE Main 2022 question. I have not touched on elliptical motion. We'll do it somewhere, some other time. Elliptical motion is something very similar. When we get into the gravitation chapter, we'll study the elliptical motion in detail. So maybe we'll leave it for then, for that time rather than now. So we are short of time, so we're going to skip that one. We'll cover that in the gravitation chapter. But right now, let's focus on the circular motion. So let's do these problems. 5 problems will do. Start.
So it's the option.
C option. Okay.
Yes, sir. C is fine.
C is fine. Okay. We have not spoken about the time period. Time period means time it takes to make one complete revolution. So, what will that be, Chavi Beta? So, you are given the speed is v, radius is r. So, how much will be the time period? Or you can take angular velocity instead of the linear velocity v. What will be the time? Now, what is time period? Time period is, or speed. Speed is distance by time. So time is distance by speed. So how much distance does it travel? Does it
So 2 pi r.
2 pi? Wonderful. So 2 pi r divided by speed v. So 2 pi r by v.
Yes, sir.
Okay, in terms of omega, so how will you write that, beta? So it will be again 2 pi r divided by v. V is omega r. So 2 pi.
Yes, sir.
Oh, wonderful. Okay.
So 8 is to 1.
Okay. Ruchika, beta.
Yes, sir, it is one.
Any particular reason, beta, why it took so long? That's fine. For the students on YouTube who might be listening this lecture, so we are solving certain questions, which is a typical norm. That's how we do it. So we are focusing heavily on solving questions because that's what matters. Only when you learn to apply the concept, that's where the value add, true value add is happening. So what we typically do is we try and solve 5 questions to 10 questions during the class. Today's class, because the theory took much longer, so we are trying to wrap up 5 questions.
Sir, 20.
Let me get back into the online class. 20, okay? Rate of change of kinetic energy. So 20 kilogram meter square per second. So, beta, just to make sure that we are on the same page, so kinetic energy beta is half mv square.
Yes, sir.
So how would you write its rate of change? Can I write like this? Half m 2v dv by dt. Yes?
Yes, sir.
Okay. And what is this v? We're talking about speed here. So mv dv by dt. Right, Ruchika beta? Is that how you have done it?
Yes, sir.
Okay. So what is dv by dt beta? How much by what amount at what rate? So you have picked this value or you have taken the magnitude of the acceleration beta?
Sir, I just did dot product of the velocity and the acceleration.
You've just taken the dot product of. Okay. So you have used the definition of the your work done. So dk by dt. Is that how you have done it, Peter?
Yes, sir. Sir, F dot V. So, sir, MA dot V. So, it's the same thing only.
Yeah. So Peter will cover this in the third chapter, the work energy power. So where we'll study that the power is the rate of work done. So how much work you do in 1 second. And work done is defined as a scalar product of force and displacement. Right? So F dot ds. So when you divide by dt, you get F dot V. This is your power, rate of work done. And we know from the work kinetic energy theorem, something we'll study, that if the net work done by all forces, conservative and non-conservative put together, that will give you the change in the kinetic energy. So dW is equals to dk, change in kinetic energy. So if you do that, then you can write dk by dt is F dot V. Ruchika, if you were to follow it, do it from our standard method, that dk by dt is mv dv by dt, and now we are interested in this is the rate at which speed is changing. Speed is changing at this rate, 20. Correct? No? This is the centripetal acceleration 10. Right? If somebody were to ask you how much is the radius, then you could have figured that out. Right? V squared by r is 10. But anyway, so mass is how much? Mass is 100 grams or 0.1 kg. So V is 10. And this is your 20. So what do you get? 20 kilogram meter square per second cube. Chavi beta, is that clear? Yes, beta?
Yes, sir.
सर आपने सिर्फ 20 से क्यों मल्टीप्लाई किया?
Okay. Beta, kinetic energy is a scalar quantity defined as half mv square. What is v there? The magnitude of the velocity vector. Yes?
Yes, sir.
The rate of change, so that will be mv into dv by dt, rate at which the magnitude is changing. Correct, no? Yes, beta? Magnitude is changing.
Yes, sir. Huh.
Right? Now, if you have 10i and 20i plus 10j cap, right? So let's say this is I, 10i, this is your velocity vector. Is pointed towards the x direction. If you assume the x direction is towards the right, then your acceleration vector, if I were to draw it in a slightly different color, so it is in this direction, it is 20i, and in this direction, it is 10j. Correct, Namita? Now, the acceleration that is perpendicular to the velocity vector, that is only gonna try and change its direction, only will try and rotate it. It cannot change the magnitude. To change the magnitude, the acceleration has to be in that direction. So in a very small, let's say in a microsecond or a millisecond, right? What's going to change the magnitude? Well, the component of the acceleration that is in the direction of the v. The one that's perpendicular, that will only slightly try and rotate it. Yes, it cannot change the magnitude. And what are we interested from the kinetic energy standpoint? We're interested in the rate at which the speed is changing, the magnitude of the velocity is changing. Yes, no, scale of 1 to 5.
हाँ सर थोड़ा समझ आ रहा है
समझ में आ रहा है? Okay.
Yes sir.
Let's do one more problem and then we'll stop. By the way, you guys have some time to carry on for maybe another question or two, or do you guys want to stop fairly quickly? Let's do this. This is our last problem and then we'll take a break, okay? Let me just quickly JEE advanced question if there's something interesting in there. This is the 1999 question and okay, this is more of a elliptical motion. So maybe we'll not cover that today. So let's go back to the NT Abhyas question. So question number 2. Let's do it. Okay, for the students of the YouTube, we're gonna stop the class. We're gonna wrap up this question, and then we'll carry on with the class tomorrow. So once again, the classes happen from Monday to Thursday, 5:15 to 6:15. Sometimes they run a little bit longer. So hope you guys have a great evening, and I'll see you guys tomorrow.